Okay. Um, Now, what I'm going to do is, since you guys are so bad about asking questions in class, I'm going to ask them for you. So I'm going to preemptively discuss uh, certain homework problems, and then we'll see if you have questions about any of it. Okay. I'll just allow the chalk again.
I don't know. I pulled it
Oh,
up.
okay. This chalk is good. Yeah, the piece is really, really smooth. It's a good one. I don't know why it's going to be like this one right way. Okay, so first one I'll discuss is 3 to 20, and the number probably doesn't mean much to many people, but we're writing the function solve AXB. Now, solve AXB by itself does very little. It delegates to other functions, one for Gaussian elimination, one for forward substitution, one for back substitution. But the a previous problem that calls for implementing Gaussian elimination does not include any kind of pivoting. This problem requires Gaussian elimination with pivoting. So tips on pivoting or implementing partial pivoting in MATLAB. Okay. So now the thing is, so we want this factorization, PA is equal to LU, where P is a permutation matrix. So your outputs, so your Gaussian elimination function outputs will be LU. Now that's from before. Like there's a previous problem where you implement Gaussian elimination and you store the interesting part of L in the lower triangle and then U in the upper triangle. So that's still going to happen. And then P, so this is an indication of which row interchanges are made. But there's one key distinction between what happens in code and what happens in mathematically. So mathematically, P is a full-blown n by n matrix where you have rows of identity interchanged. But not in code. P is a vector of indices from 1 to n. So the order of the indices tells you the order in which the rows had to be scrambled during Gaussian elimination because of partial pivoting. Now, the reason why this is a good way to go, there's two reasons. One, storage. Storing P as a permutation matrix explicitly, you have n squared entries. All of them are 0 except for n of them which are 1. That's really, really wasteful. The second thing is, advantage is it makes it easy to handle the next stage, forward substitution. So you solve, now mathematically, it's Ly is equal to P times B. In other words, just as you had to scramble the rows of A, you're also scrambling the rows of B. But in MATLAB, what you're doing is you're calling your forward sub function from a previous problem with your matrix L. Well, really it's LU, the matrix that comes back from Gaussian elimination, because the entries of L that you need are already sitting in the lower triangle. You don't have to extract the lower triangle from it. Just pass it as is, because the forward substitution algorithm only uses the lower triangular entries of whatever matrix you give it. It never touches the upper triangle. So it doesn't matter whether there's zeros there or ones there or complete garbage there. It doesn't matter. So that's the matrix you'll use for forward substitution and back substitution. because back substitution only touches the upper triangle. So that's the matrix you'll use. And then how you handle taking the entries of your vector B and you want to scramble those in the same way you scramble A. The easiest way to do that in MATLAB is this, B of P. Because what that does is it takes the indices from P and it extracts the elements of B in that order. So this is this. Just the easiest way to do it in MATLAB. Because MATLAB, what you can do is as an index, if you pass any row vector of indices, assuming all those are valid indices in range, it will retrieve elements according to those indices. For example, B1, 3, 2 gives you a vector that has B of 1, B of 3, B of 2. So it's a very convenient feature of MATLAB that you can just use any row vector, doesn't matter where it came from, as a vector of indices into a vector or matrix. So that's how you handle that. So that's one reason why we're using this vector of indices instead of a full-blown matrix, not just for storage, but also this is a lot more efficient than doing this, which is a matrix vector multiplication, which just takes order n squared operations. We don't want to do that if we can avoid it. Okay, so that's what's happening outside of Gaussian elimination. That Gaussian elimination will return to you this permutation vector P. Now, I need to explain to you within Gaussian elimination, like suppose we've already implemented Gaussian elimination without pivoting. How do you add pivoting to it? It's a pain. So try to make it a little less painful. Now, mathematically, what you're trying to do is swap row J, and because you're examining each column J from 1 to n, or n minus 1. You swap row J with row, I'll call it P, Q, where AQJ is equal to the maximum over all indices, row indices from J down to the bottom, J to N, of A, I, J. In other words, what you're doing is, if you're in column J, you're looking at all entries from the diagonal on down. So you're looking at this, and you're looking for the largest one in absolute value. And once you have a row index, so if the largest element is here, that's in row Q. So now these rows, row J and row Q, are going to be interchanged. Okay, now, how do you do this in MATLAB? You can use the max function. So max, if you give it a vector, it'll give you the maximum vector. But sorry, I need to erase this and put the outputs in. So if you give it any vector, which in this case would be the appropriate portion of a column you want to search in, and don't forget to take the absolute value. You want to take a maximum of absolute value. Now, normally the default usage of max will just give you the maximum element, but you don't really care what the maximum element is. You care where it is, what index, because you want this index Q. So there are two outputs you can use here. So the maximum value is the first output that it'll return. and then the index is the second output that it'll return. So that'll tell you where within that vector the maximum is found. Now, keep in mind, index will be a number between 1 and the length of this portion of a column. Now, that is going to be n minus j plus 1. Okay. Now, because that's the length of a vector that got passed in. But Q is not in this range. Q has to be an index between j and n. So once you get the index out of this, to get Q, you have to correct it. So now you can see from here and here how to correct it. I'm not going to tell you. Figure it out. Okay. So once you've identified the row you're going to swap with, which might be nothing, it might be equal to j, then you don't do anything. Then, as far as carrying out the actual swapping, again, use row vectors of indices. So, for example, you want to swap rows in A, and you also, okay, so I need to make this note here. And P is your vector of indices. Initially, you haven't swapped any rows yet. So it'll just be the indices 1 through n in order. And that's the way you do this in MATLAB, 1 colon n. That's a range of indices from 1 to n. So that's what you would set it to initially. But now you have to swap. I'll show you how to swap in P, and you do something similar for A. Now P is a vector. So you can just say JQ equals PQJ. That's it. That does the swap. Okay. Now, you want to do the same thing in A, but keep in mind, A is not a vector. A is a matrix. When you refer to entries in a matrix, you got to refer to rows, comma, columns. So you're only going to do this swap on the rows. And you want to make sure to swap the entire rows. Now, this is something that I wish I could take more time to explain, but remember, in A, you're storing your multipliers in the lower triangular part, and the result of Gaussian elimination is sitting in the upper triangular part. So when I say swap entire rows, that means you're swapping the part of row that you're still working on through Gaussian elimination, and you're also swapping the multipliers. That's intentional. That is needed to make this correct. So, because if you're saying you're going to swap a row, or swap 2 rows, then the multipliers that you've used in the past on those rows, they have to be swapped also. Because one thing I discuss at length in the book, I think it's actually not in the notes, is this. That when you perform pivoting, you start with your matrix A. I might have done this before. I think I did write this on the board before, when first covering it. You first do a permutation matrix to swap some rows, possibly. Then you do a row operation, like adding a multiple of a row to another row. Then another one, another permutation, then more other row operations. And you keep going to get your upper triangular matrix U. Now, notice you have permutations interlaced with other row operations. But L is supposed to be M1 inverse, M2 inverse. All the inverses are put together. So if these are alternated like this, I can't rearrange these. I'm not allowed to do that because matrix multiplication is not commutative. So how can I justify, because I want this factorization, PA equals LU. I can't simply take all these permutations and move them up front. Well, actually, okay. I can't just move them here and then move the m's over there. I'm not allowed to do that. However, and this is what was I've derived in the book, I can move these p's over here in front of A and move the m's, shuffle them off to the left, if I change the m's accordingly. And the way I do that is by swapping entire rows. So that is what makes that work. Because basically what you're doing is you're applying, if I want to move this M1, like if I want to move it over here, I can do that as long as I apply like P2 on the left and P2 transpose on the right. There's a trick like that to make it work. But I don't need to get into the technical details of all that. I can just tell you in your code, just don't forget to swap the multipliers as well as the rest of the row. So swapping the entire row, including the multipliers, makes everything correct. So for now, you can take my word for it that it's magic, and then you can look at the book later to see that it's not. Well, okay. So you can follow this to implement partial pivoting in MATLAB. So good luck with that. Well, this is an optional assignment. But okay. What are any questions about that? I'm going to talk about a couple other problems, but any questions about this problem? All right. Where's the Bhagya? Okay. Oh, okay. Well, you can watch the video. Okay. All right. Now, there's two other problems I want to discuss. That discussion will not take as long. So the next one I'll say a few words about is 3.3.8. Show the following. If A is a symmetric positive definite matrix, so is A inverse. Okay. Now, so I'm going to, basically what I'm going to do is I'm going to restate the problem in a more helpful way. Really this is good advice for doing proofs anyway, is if you're asked to show something like this, show A inverse is symmetric positive definite, you want to go from that statement to an equation that you want to show holds. In this case, that equation comes from, and how do you get that? Using definitions. In this case, a definition of symmetric positive definite. So equivalently, show that Y transpose A inverse Y is strictly positive for any vector, any non-zero vector Y, okay, given that X transpose AX is strictly positive for any non-zero vector X. And there's a reason why I use X in one equation and Y in the other, because They don't have to be the same. Like if you want, you can think of it in terms of using this as your starting point and getting from that to this. Okay. And you have to use the fact that A is non-singular. I talked about this in relation to a previous problem that AX is equal to 0 if and only if, or sorry, well actually I can write either way. Only if, so AX is non-zero if and only if X is non-zero. Okay, so I've thrown out some breadcrumbs. So see if you can pick them up and find your way home. And was 341 was the other one? I remember. Well, I know 341 came up last time, but I think I remember something else to say about it. Oh, unless I'm thinking of a wrong problem.
The one where it says A is non-singular,
Yeah.
Yeah, A is non-singular if and only if X isn't zero.
Um.
You said try using contradiction.
Oh, right. Yeah. To show that A plus epsilon E is non-singular. Okay. So if you assume that A plus epsilon E, okay, so 3, 4, 1. A plus epsilon E is singular. There exists a vector X such that A plus epsilon E X equals 0. So what you can do is, now I mentioned you can use properties of norms to show a contradiction. And the thing is, if you have any equation like this, you can take the norm of both sides of it and then use various properties of norms that are given a definition to manipulate. I have to mention, this is important. X has to be non-zero such that this is true, because if X was 0, then of course it'd be 0. That's a key ingredient in the problem. Now, you would not take the norm of both sides of this equation. That won't help you. But if you do some rearranging, so try some rearrangements and taking norm of both sides and see what you can do. So you're using properties in the, like from a definition of a matrix norm that I covered in class. So see what you can do with that. And I will take any other questions that anyone might have. Anything at all? Of course not. Easy peasy, right? Okay. Of course, obviously it depends on how many people do this assignment, but yeah. Okay. Now, during the rest of the time, I'll return to chapter 4. Seems like a monster emerging or something. Okay.
It's so cold in here.
Yeah. Well, yeah, because it's summer now. Did you get the memo?
Apparently.
So Mercury cracked 70 degrees.
Pick a temperature. Your just pick.
Okay. So I will spend one last class period talking about QR factorization because I'm sure you're not sick of it already. But there's just so many ways to compute it. Okay. And now I have to show you the worst one. Yeah, because I mentioned how when you have multiple methods of solving a problem, there's no clear winner. And while this is not entirely without its advantages, I still say it's called a clear loser. All right, so QR factorization. By Gram-Schmidt's orthogonalization. So this is 6.3 in the notes, 4.2.3 in the book. Actually, I should make sure of that. And I remember learning about Gram-Schmidt orthogonalization in my first linear algebra course. Something I would never show up in the first linear algebra course here, but that's never matter. The second one maybe, but we haven't offered that. Okay, but I remember my classmates and I would call it by a different name by omitting the M, the second M. Yeah, Gram-Schmidt. Yeah. Okay. It's actually 6.4. Okay.
That is so irritating.
Well, some of these days ruined. Okay. Now, this is actually used to compute a different sort of. Shut up already. Thank you. All right, a different sort of QR factorization that we've seen from Householder Gibbons cases. So we have full QR factorization is what we've been working with. So A is m by n, Q is m by m, and R is m by n. But I've shown you Q and R both broken down. So like we have Q1 and Q2, it's broken down by columns. So we have the first n columns here in Q1, and then everything else in Q2. And then R breaks down by rows. So R1 is n by n, non-singular, and then we just have zeros down below. So if you're using householder reflections or Gibbons rotations to perform a QR factorization where you apply them on the left to A to reduce it to upper triangular form, you get this full R here, and you also get the full Q. But Gram-Schmidt does not do that. So the thin, or economy size, QR. So we just factor A into, really it's just the Q1 and R1 from here. So Q1 is the same size as A, and R1 is a square matrix. R1 is upper triangular and is not singular due to our ongoing assumption about A, that its rank is n linearly independent columns. And Q1 has orthonormal columns. So Q1 transpose is still equal to the identity. But remember, keep in mind here, we're assuming that M is greater than N. So Q1 is not a square matrix; it's a tall, thin matrix. So it doesn't go the other way. Q1 transpose is not identity. So
I'm not thin. I'm not the thin QR. I'm the full QR. That's also not very much.
oh, well, okay. Anyhow, so,
I'm tired of delirious.
we all are. Okay. Now, so really what Gram-Schmidt is for, the reason why it's called Gram-Schmidt orthogonalization is you can think of A as just a collection of n vectors that you're given, and you try to get from those n vectors an orthonormal set of vectors. So orthogonal, that are perpendicular to each other in n space, and normalized, so they all have they're all unit vectors. So this is a test that comes up in other problems besides just the ordinary least squares problem, where you want to orthogonalize a set of vectors, and that's what Gram-Schmidt does. It just happens to give you this portion of a QR factorization, and this is perfectly fine for solving the least squares problem. So in least squares, once you've done this, you solve R1x is equal to Q1 transpose B using back substitution. So, you never needed the rest of Q anyway for this. Okay, so how do we carry out Gram-Schmidt? So given this set of vectors that are columns of A, how do we get vectors that span the same subspace as the columns of A, but they're orthonormal? So really, Gram-Schmidt produces from the columns of A, so A1, A2, AN, an orthonormal basis which consists of these vectors, Q1, Q2, Qn. From a subspace that is span, so the subspace is called span of these columns of A. Now, if you forget what span is, or maybe you didn't learn it because you didn't take that class. Again, one thing that's supposed to be covered in a linear algebra class, but I can't trust anything being covered in linear algebra class here at USM. So I think we all know why. So this consists of all linear combinations of these vectors. So all of them. So the set of all linear combinations of these, A1 to AN, is the same as the set of all linear combinations of the cubes. All right. Now, so before I show you how you get the Q's from the A's, I need to I'm going to tell you a story about when I covered this topic back several years ago when I was still at Stanford. So my friend is a faculty member out there, Margot Garrison. She was teaching a course on numerical linear algebra to an auditorium of 200-something mechanical and engineering graduate students. And she needed me to substitute for her one day. And the topic was this, Gram-Schmidt orthogonalization. And the thing is, when I was preparing to cover it, I was thinking, well, Gram-Schmidt is used to compute the QR factorization. So I referred to my original vectors as A1, A2 up to AN. And then the new produced vectors as Q1, Q2 up to Qn. But then when Margot gave me her notes on this topic, I'm reading through them, and I was like, she used different letters than A and Q. I was like, why did she do that? And I didn't have a chance to ask her about it. I thought, well, I mean, I've covered this topic several times. I'm just going to go with what I know here. So I'm computing A equals QR. So I come to class and I do all that. I do what I'm about to do with you guys and show how to get these from these. So I'm writing A's, AJ's, and QJ's all over the board. And I get to the very end, and a student asks me, that they could not tell the distinction between something like, for example, A1 and Q1. Because that's supposed to be the tail of a Q. And that could not be distinguished from the shorter tail of the A. And this was all over the board, that the students had no idea what on the board was an A or a Q. I got so pissed, I just threw my chalk up in the air. It's like, oh my God, well, my goose is cooked. What the hell am I supposed to do with this? Because, I mean, and that student had waited until the very end of the presentation. I spent like an hour working on this, covering the whole board in 200-seat auditorium, and now everybody's confused. And it's like, yeah, so that is why.
So is that, are those A's or Q's?
Don't worry, I'll do it.
And this is why, as I go through a presentation,
Because AQA.
I will exaggerate the tails as much as I need to, so that there's no ambiguity. So if anyone asks me that question, you flunk, because you can't even read the alphabet. Okay, but I thought it'd be good to warn you up front, just in case. So that way you can do better by me than they did. Yeah, and when I told Margot after what happened, she said, yeah, that's why I used these different letters. It's like, oh, yeah, thanks for telling me. Yeah, so that was fun. Okay, so, because, it's the QR factorization. It's not the, PZ factorization or something. So it's really a fault of whoever named these things. And we all know that these things are named very strangely anyway. Okay, don't want that. Okay. So I can show you, like from the ground up, like how we get the first vector, second vector. And I can show you the pattern from there. All right. So the idea is for each j going from 1 to n, we have the span of the original columns, A1 up to AJ, is equal to the span of the corresponding orthonormal vectors. And we maintain this assumption from j equals 1 on up. And these have to be orthonormal. And what that means is Qi transpose Qj is equal to this expression, the Kronecker delta, which, in case you've forgotten, is equal to 1 if I is equal to j and 0 otherwise. Whoops, I didn't make my tail long enough. All right. Now, so the thing is, when j is equal to 1, That's very easy to do because you only have one vector. You don't have to check whether it's in a product with anything else that's going to be 0. You only have to make sure that it's normalized. So in j equals 1 case, we just set q1 equal to a1 divided by its vector 2 norm. So if there's nothing it needs to be orthogonal to, and this makes it normalized. And to confirm that, if I take q1 inner product with itself, so that's going to be a1 over its 2 norm, transpose, same thing. So that's going to be a1 transpose a1 up top. And then I have the 2 norm squared down below. But a 2 norm of a vector squared is the same as a dot product or inner product with itself. So they cancel, and you get 1. So that's all you have to do to normalize a vector. You just divide by its vector 2 norm. Okay, so we have a start. We have our first vector in our orthonormal set. Now, we move to j equals 2. So we need to get q2. So q2 has to be a vector that is in the span of a1 and a2. That's the linear combination of those two vectors. But it also has the property that must be a unit vector, and it must be orthogonal to q1. All right. Now, I'm going to use a definition of span here to give myself a form for q2. So I need some concrete expression for q2 to work with. So now I can actually get that concrete expression from the QR factorization itself. Because if A is equal to Q1 R1, that's the same as saying that A1, A2 up to AN, that's A, is equal to Q1, Q2, Qn, R1. So I fill in the entries of R1. So that'd be R11 up here, 0, and then R12, R22, and then I keep going. All right. And in fact, so what I can do is I can actually look at this matrix equation one column at a time. So first column, I have A1 is equal to Q1 R11. So look at the first column of this. The first column of this whole thing would be the first column of R1, which is just this, times these. So I'm multiplying all these by the Q's and adding them up. Well, we're all 0, except for the first one. So in fact, I can tell you what R11 is from before. R11 is equal to the 2 norm of A1. And you can see that from what I did over here. I'm just rearranging that. Now, I can go to the second column. should have done this from the beginning, but whatever. Actually, did I do that in the book? Oh, yeah, I did. Silly me. Okay. A2, second column of the left side, equals the second column of the right side, which is, again, all zeros except for the first two entries. So that's going to be Q1 R12 plus Q2 R22. So I need to solve for these. So the way I can do that is I need to take the dot product of both sides of this equation with Q1. So on the left side, I'll have Q1 transpose A2. And then here I'll have Q1 transpose Q1, R12, plus Q1 transpose Q2, R22. Here's where we use the fact that the Q's must be orthonormal. Gone. Q1 and Q2 are orthogonal, so that's 0. So R22 is out of the picture. This Q1 transpose itself is 1. So now I have R12. Just pops out. R12 is the left side. Q1 transpose A2. Okay, so I'll box the entries that we have so far. Okay. Now, so I have R12, but I still need to solve for Q2 and R22 are still unknown. And the thing is, having those two unknowns, that complicates matters until you realize what properties Q2 is supposed to have. Q2 has to be a unit vector. So here's what I can do. Q2 times R22 must be, I have to rearrange. So it's going to be A2 minus Q1 R12. So now I have like the general direction of Q2. It's just that now I have to, so I have to take this and make it a unit vector. So to get that, I can just normalize this. So Q2, so actually here's what I'll do. I'll set R22 equal to the norm of this. Because if I take the norm of both sides of this equation, the norm of Q2 is supposed to be 1. So all that's left is R22. So R22 is the norm of this vector. So because the norm of that has to be 1. That's what tells me that. Okay. So then, now that I have R22, I can just divide to get Q2. So that means that Q2 is equal to this vector that I have on the right side divided by R22. Right. So questions about how I got Q1 and Q2? So from there, I can show you the general case by taking an arbitrary column, column J, of this matrix equation. Are we all keeping our A's and Q's straight?
Yes.
Okay. I thought so.
We're smarter than those Stanford
Well, you know, sometimes you see these things like on Facebook or wherever, like 5-year-olds could solve this, but Stanford students couldn't, and all that. Yeah, and when I saw that, I'm like, hey, and then I solved it.
And then I solved it. I spiked you. That's
Yeah.
okay. I am not smarter than a fifth grader.
Which of the entries are unknown? Is it the Q's or the R?
Oh, well, at the beginning, they're all unknown.
Oh, okay.
Yeah, because in the beginning we only had A, and we have to get both of these, and the only reason we can get both of them is from the properties of the cubes that they have to be orthonormal. And you'll see that here when I go to column J. So notice Q1 was pretty straightforward. All we had to do was normalize A1. Q2 took a little more work. We had to subtract something off first, and then we can normalize. So that's good. We had to subtract off a bunch of things. So the left side of the matrix equation over there is AJ. And then the right side is going to be Q1 R1J plus Q2 R2J, and so forth, up to QJ RJJ. So at this point, so Q1, Q2 up to QJ minus 1 are known because they were computed from handling earlier columns of A. Dang it. That was unpleasant. But we still need this last Q, which is not yet known, and all of the R's are not known either. Because we computed R up to column J minus 1, but all of these entries are in column J. So to get the unknowns, I can do the same thing I did over there. Because what I did is I took the inner product of both sides of this equation, but over there I did with Q1. So for K strictly less than J, I'll do QK transpose AJ. Because K is less than J, I know what this is. So then I'll write this as a sum. I equals 1 to J of QK transpose QI RIJ. Okay. So all I did was I took the dot product of both sides with QK each term, and I just expressed the right side as a summation because I'm lazy. Okay. Yeah.
The Q1, Q2, the small ones, are they numbers or they are vectors?
They're vectors. Yeah, because they're the columns of Q1.
Okay, so they are like row vectors.
Oh no, but they're column vectors.
Column vectors, yeah.
Yeah.
Okay, so that looks like what is a matrix.
Yeah, so this is Q1,
Okay.
and that is A. Yeah, so anytime I write a matrix like this, I'm breaking it down in terms of its columns. So I can work with each column individually. Sorry about that. And then this whole thing is R1. But there I'm looking at the individual entries of R1. You have a question? All right. Okay. Now, this is equal to 0 if K is not equal to I. So, and it's equal to 1 if K equals I. So in other words, all of the terms in the summation disappear except one of them. provides this summation bloodbath is RKJ. So now I have almost all of the R's. All of them except the last one, RJJ. So for that, so now I'm going to take all these terms, because now every term on the right side is now known, except the last one. So I'm going to rearrange. So I'm going to have QJ, RJJ is equal to AJ minus all these other terms. QI, RIJ. Just getting too cluttered and move this over here. All right. Now, if I take the norm of both sides, well, the norm of the left side is just RJJ, because QJ is a unit vector. So actually going to box this. So that's how I get my diagonal entries. Oh, actually, I should have done the same thing over here for R22. Okay. And I'll just write it over here. I'll just repeat that. So QK transpose AJ. So those are the off-diagonal entries of R, like the entries above a diagonal. Okay. And then I can just, so I can take this vector in here and normalize it, or in other words, divide by RJJ to get QJ. So QJ is equal to this vector, AJ minus this sum. QI, RIJ, all over RJJ. All right, so now I have my jth orthonormal vector, and I can just keep going. So showing how to do it for general case for an arbitrary column. So for the first column, for j equals 1, the sum stops at j minus 1, so you don't have anything. But as j increases, you have more terms subtracted off. So each qj takes more and more work. Okay. Oh man. Yeah, I just saw like in the book. I mean, it's correct. It's I use the indices differently here than I did in the board, but I like this better. I should change the book. But
It is yours.
what?
Second edition.
Yeah.
It is yours.
Well, I'm finding mistakes every day, so after going months without finding any or no one telling me about them, all of a sudden they're coming out. It's like,
Did
gee,
you have
thanks.
somebody read over it for you?
Yeah, but I didn't know what they were doing. Okay, but yeah, things I read it through it, and I did fix many things, but oh god, it's embarrassing. But yeah, unfortunately, things slipped through. Yeah, like J there is K here, and I there is J there, and oh god, what was I thinking?
Take a picture for it.
Yeah. Well, I'll remember, but because I have to make sure, like, if I change that, I got to make sure that I don't cause confusion somewhere else. Yeah.
You'll change it.
Okay. And the funny thing is, now I'm going to write the algorithm, and the algorithm in the book is indexed like this. So, yeah. So I'm probably going to catch some shit over that section. Okay. All All right, so summarize. So here's the actual algorithm. In a way that could be coded in MATLAB, and actually is one of the problems in the chapter 4 homework. Okay. So this is called classical Gram-Schmidt, or CGS. Now, it's not the same as the classic Coke, New Coke thing, because in that case, classic Coke is better, but this is not. It was just invented first. Okay, so what you do is, so you work with each column of A from left to right, like in other algorithms you've seen all semester long. And what I'm going to do is I'm going to, because notice we keep subtracting things off from AJ. So I'm going to make a new vector, I'll call it V, that's equal to, starts off being equal to AJ, and I'm going to keep updating it. Okay. And to subtract things off, I have a sum there that goes from I equals 1 up to j minus 1. So I'll do that as a loop. And I'll compute my entries of R, Rij. Wait. Okay. Instead of K there, I'll have I here. So Q I transpose AJ. And then I update V. So now that I have this term here, I'm going to subtract it off. I'm carrying out this. So V equals itself minus Rij Qi. All right. So then, once the loop is complete, V is just this vector here. So to get the last element in this column of R, all I have to do is say Rjj is just the norm of V. And then to get the last Q, that vector in the numerator, that's V. So I just got to divide it by Rjj. And that's it. That's the whole process. Now, this Gram-Schmidt algorithm is the one that is taught in typical linear algebra classes. I say typical, then not ours, but it's supposed to be. And sort of thinks, okay, that's fine. It works. But remember, this is a numerical linear algebra class. So there's computer arithmetic involved. And the problem with this classical Gram-Schmidt is if A is nearly singular, meaning the columns are almost linearly dependent. In other words, one column, or at least one column, is almost a linear combination of the others. Put another way, A is very badly conditioned. So if that happens, you get catastrophic cancellation in V, because V is going to be nearly zero after you subtract off. Like, for instance, if the first three columns are almost linearly dependent. Then when you get to the third column, you subtract terms involving the previous two columns off of V. V is supposed to be nearly 0, but you're computing something small from items that are larger. That's the definition of catastrophic cancellation. You're subtracting relatively large numbers. You're subtracting relatively large numbers and expecting a small result. What that means is this V from floating point arithmetic is going to be highly erroneous. So that just throws off everything. So that's why this algorithm that's taught in linear algebra classes almost everywhere. I'm just not letting it go, am I? No, I'm not. Is it's actually not a good one to use. So no one would ever use this in a practical setting to perform a QR factorization, especially when they have the option of performing householder or Givens QR that's much more numerically stable, even though that's a full QR factorization, not the economy size. Now, there is a way to fix this. And so, now here's the funny thing, is the way this modification is normally described can be quite lengthy. I'm going to try to condense it. I also don't have too much time left, or very much time left. So, notice the original algorithm. We compute the entries of R column by column. So, first column, then second column, and just keep moving left to right. But the thing is, once we have Q1, for instance, after we're working on the first column, we actually can compute all the entries of R's first row. Now, this algorithm doesn't do that. It waits for those entries to the right until later. But we could compute, so once we have Q1, we can get all of the first row of R immediately. And so we can compute the entries of R in a row-by-row fashion rather than column by column. Or put another way, that from this equation, AJ is equal to Q1 R1J plus Q2 R2J and so forth up to QJ RJJ. Now, how did we get the entries of R before? I would take the dot product of this with one of the Qs. But the thing is, okay, make sure I describe this carefully. Because the thing is, R2J, which this algorithm computes as a Q2 transpose AJ, is also equal to Q2 transpose AJ minus Q1 R1J. In other words, if I've taken AJ, subtracted off a contribution of Q1, so now I have this updated vector, it doesn't matter whether I take the inner product of Q2 with the original column or the updated column. Why? Because Q2 is orthogonal to Q1. This contributes nothing. it makes no contribution to R2J. So the thing is, if I'm telling you that it doesn't matter which one of these vectors I take the inner product of Q2 with to get to, and the classical Gram-Schmidt uses this one, so now you're wondering, well, what's the advantage of this one? For one thing, it has a smaller norm. So remember, catastrophic cancellation results from subtracting large numbers and getting small results. So if the numbers we're subtracting are already made smaller to begin with, that reduces the cancellation error. So it's actually advantageous to work with the updated column of A than the original. And so there's two ways to look at this. Way number one is I go ahead and compute the entries in row 1 of R as soon as I can. So compute the entries of R in a row by row fashion instead of column by column. And once you do that, you can subtract off these contributions. So that's one way to describe what's really going on here to try to make this work. But the easier way to see it, the thing is, it's really easy to implement this in the algorithm because all I have to do is change this to QI transpose V, not AJ. So this dot product is always with the original column of A. This inner product is with the updated column of A, where I've subtracted off terms that would not contribute to Rij anyway. So by computing this dot product, where the norm of V is guaranteed to be less than or equal to the norm of Aj, by taking inner product with a smaller vector, I reduce the cancellation error. So this is called, this with a change, called modified Gram-Schmidt, or MGS. So any practical implementation of Gram-Schmidt would use that instead of the classical because of the improved round-off error aspects. Okay. All right. Now, how well does this actually work? And the answer is, it's still not that great. But it's definitely an improvement over classical. So to give you an idea, and I'll stay out, I don't have much to write here, so I can stay out the square zone. So let Q1 hat be the computed Q1 when you're trying to get the QR factorization. So Q1 transpose Q1, as I mentioned at the beginning, is supposed to be identity. Now, if you're using modified Gram-Schmidt, what we can say is that Q1 hat transpose Q1 hat minus identity, which is supposed to be 0, but so the theory behind this indicates that it's proportional to U. Okay, U is the. Whoops, I should declare zone. Sorry, I'm burning out. U is the unit round-off, also known as machine precision. In other words, it's the smallest relative error that you can expect from floating point arithmetic. So in our usual IEEE system, it's 2 to the minus 52. So like, okay, no one cares what that is. It's 2.2 times 10 to the minus 16. But this is a condition number of A. So if A is badly conditioned, this error could still be large. Whereas if you are using householder reflections, this same error is roughly just U by itself, no condition number. So even if A is a horribly conditioned matrix, your Q1 hat will still be very accurate. And the reason why is Q1 is obtained by multiplying by orthogonal matrices, householder reflections. Those are perfectly conditioned. So that's why it all works out well. Unfortunately, I don't have a similar result for Gibbons rotations, but I imagine it's similar to this for the same reason, that you're performing orthogonal transformations that are perfectly conditioned. Okay. Now, but as far as computational cost, I should have left room for that here. So the cost in terms of floating point operations with modified Gram-Schmidt is, let's see, 2mn squared. And then householder let's see, we have 2. It's actually roughly double that. Because if you want Q1 of householder, you have to apply these household reflections to the left of A, just reduce it to upper triangular form. And then you have to accumulate all those transformations if you want to explicitly construct Q1. Because if all you cared about was getting R, then you'd have only 2mn squared. Householder is actually the most efficient method and the most accurate for just computing R, or R1. But if you want an explicit Q1, modified Gram-Schmidt is the most efficient way to go, even though you have a little accuracy problems there. Okay, so, but all three of these methods, householder, Gibbons, Gram-Schmidt, can be used to at least solve the least squares problem. But I've given you reasons to choose any of these methods over the other. But it's when the thing is, for solving least squares, you never need Q1 explicitly. So it's usually that. So to actually take give a set of vectors, like columns of A, and generate from them a set of orthonormal vectors that span the same space, and do so generate them explicitly, that's really the main reason you want to use Gram-Schmidt. If not, if you have some other QR application, like solving least squares, most for general case, probably householder. In some special cases, Gibbons is the best idea, the best approach. Okay. Actually, one of the problems I did not assign from chapter 4, but I just wanted to point it out. I'd actually concocted a matrix where that's nearly singular, where if you try both classical and modified Gram-Schmidt, you actually get visibly different results. So it's something that can happen, at least in toy cases that I can contrive. But the theory says that that's what can happen. And if you can be applying this to any matrix out there, you just don't know where it comes from. You can't make any assumptions about it. Sometimes these bad things can happen. And that's why numerical analysts don't look into these things before something literally catastrophic can happen, which unfortunately sometimes has. I mean, and I tell this whenever I teach the undergrad numerical analysis class, people have literally died from failure to take into account floating point arithmetic issues. So can't say that math is not real world relevant. Okay. Oh, well, I only have 5 minutes left anyway, so well, I covered what I need to. So that means I won't see you for quite a while because
Oh, yeah.
I won't be here next week.
And then we have Monday off.
Right.
And then we see you.
So on Monday I will record a lecture, but that's something that can be watched later. So yeah, so the next class will be
The 6th.
Wednesday, March 6th.
Yes.
Yeah. Even after that spring break.
Yay!
So yeah, very little numerical algebra for the foreseeable future.
Maybe I can catch up.
It may be just. I'm not sure how it'll play out. It might be one somewhat longer one or 2 shorter ones. Yeah. But I'll probably do it all at once just to get it over with.
I think we are planning to meet that. And what we'll do food-wise is 2 people
So you
will
know,
split
composition and then
Johnny's the one that made that decision. I thought about it, but
So I was asking, I had to. She's asking about next Friday.